All right, so today we're going to do a review since it was requested, and also a little bit of a review with respect to Python, with respect to trees. So if you have any questions, please go ahead and post to Piazza. Again, sorry that we do not have a webcam, but at least you can still hear me today. So, where to start? Well, first of all, what are trees? Right. In fact, here, I'm just going to go ahead and grab all of this since it'll be a quick review. Let's go ahead and review what trees are, right? Trees are acyclic graphs, right? They're graphs without cycles. Now, the trees are not necessarily oriented, but we like to give them orientation because we like to associate data with them. So if you can imagine grabbing any node in a tree, lifting it out of the page, and then dangling all of the nodes down, then you would orient it downwards, and because it's oriented downwards, you could also orient it left to right. Binary trees and binary search trees in particular, each node contains a unique key or a unique piece of data or something like that. And again, it's oriented top to bottom, left to right. The root is at the very top. In computer science, all of our graphs or all of our trees grow downward, and that's because we like to read in English top to bottom, left to right. Any other way makes it somewhat difficult. Nodes may have children, and because we have an orientation left to right, you can have a left child and a right child. Limiting it to at most 2 children means that we have a binary tree, right? A tree with no nodes is known as a leaf, or no children nodes is known as a leaf, right? Binary search tree property is that everything in the left subtree has a key that is less than k, and everything in the right subtree has a key that is less than k, or greater than k, where you've got k in that node. Now, you could have trees with multiple values, right? You could have 3 5s in a tree. You just need to break ties to the left or to the right consistently. Or you can not worry about that entirely, and I'll show you this in Python, why that is an important thing when you actually go to program this stuff, that you don't allow duplicate values. If you do have 3 5s, you need to disambiguate that in some other manner in order to force a uniqueness of everything that you put into your data structure. Now you can search for nodes. To do that, you start at the top and then you go left or right depending on where you're going. This is for binary search trees, not necessarily binary trees in general. And I do mention this in the context of binary search trees because that's what we're going to focus on after this. But with at least this much background in our memory now for the review, let's go ahead and come over here to Python and let's talk about how you might end up putting together a binary tree or a binary search tree. It really doesn't matter. Well, in Python, you can, of course, define classes, right? And it's not def, it is class, right? And we need to give this a name, so we need a node class, right? The convention in Python is like the convention in most other programming languages. You go with a capital or an uppercase convention for class names. All right. Now you can go ahead and have parent, left, and right child. In fact, that's what I'm going to do because I want to set defaults. Now you don't have to. With Python, it's dynamically typed, so you can create a node without a parent, without a left child, without a right child, and then you can change that later on. You don't need like getters and setters like you do in a programming language that enforces encapsulation through private member variables. There is no private member variables in Python. Instead, by convention, as you pointed out, everything that is private is underscore. That convention actually comes from C, where you don't have the private keyword in C either. And so what you do is you prepend everything with an underscore, advertising to the world, don't touch this because you're not supposed to be touching this. This is private, right? If you do touch it then and screw around with it, then it's on you. And however you break the program, that's on you, right? But I'll go ahead and go with a parent is equal to none, right? A left child is equal to none, and a right child is equal to none, because I want those explicitly as defaults, right? That there is no left child, right child, or parent unless you set them later on. How do you do a constructor? These are called magic methods, or at least they're called magic methods in other programming languages. Are they in Python? Magic, right? Init, right? For initialization. Anything that begins with an underscore, underscore, and in Python ends with an underscore, underscore, is called a magic method. It's something that's put in there automatically by the language. There is some default implementation for it, but if you want to override that default, then you put that in here, right? It's not necessarily good defaults either, right? Every member method has to begin with self because that's the context. Like you pointed out, it's the self keyword, not the this keyword. Python does not have the this keyword, right? And then if you want to pass in data, right, because of course your node will be holding data, then this is the actual first parameter that you would provide to this function, okay? And all we're going to do here is set data, or normally we'd say this dot data is equal to data, but of course there is no keyword this, instead it is self. If you don't have self here, that's kind of equivalent, I think, to, and I'm crossing my hands here because we don't have the webcam today, or crossing my fingers, that is, because I'm not sure if this is correct, but I think that this is kind of equivalent to a static method. Maybe that's not right. But anyway, it won't work. It's not going to be a member variable. And certainly the constructor is not going to like that at all. I'm also going to add here a toString method just so that we can play around with this stuff. There is no parameter needed for this other than self. And then I'll just return self.data. Right? And that's just so that we can play around with this stuff. This str stands for, it's a toString method basically, so that you can print this thing. Otherwise, you would always end up getting an error that it doesn't know how to coerce a node into a string. So just like you can't coerce an integer into a string without surrounding it with that explicit str function. Right? Okay, that's pretty good. How do we now start creating nodes? Yeah, go ahead. Well, every node has data. My data is equal to none if you want that as a default, but you don't need a default because by putting this parameter in here, you are forcing somebody to give you data when you create a node, just like I did right here. If I did this, I believe that this will be an error, but let's find out. What is it, demo? Yep, you're missing one required positional argument data. So because somebody can't create a node without that data. Right. Let's go ahead and do it left. And by the way, there is no new keyword in Python either. Left, we'll make this into a binary search tree right off the bat. So it'll be A is the left child, B is the root, and then C is the right child. Is equal to node and C. Right. Now this does not bring these three nodes together, right? What I need to do is I need to explicitly set the relationship here. The left child of the root is going to end up being that left node. The right child of the root is going to end up being that right node that I just created. And of course, if you want to make sure that you have those bidirectional relationships so that you can actually go to the parent, right? Then you would need left.parent is equal to root and right.parent is equal to root. Right?
Wait, so everything you just have a data that you don't need to declare data, you just add to.
No, Python is a dynamic programming language. Do I need to declare int a is equal to 42? Nope. No semicolons, no types, no declaration. You just need to set it. And if you reset it to ten, it's just like PHP, right? It's dynamically typed. Whatever you set it to, that's what it becomes. All right, I could set parent to hello, right? That's not going to make any sense, and you're eventually going to have some sort of a runtime error when you try to treat this string as a node, right? But that's on you, right? That's the nature of a dynamic programming language. There are no there are no compiler errors because there's no compiler. Everything is a runtime error, right? All right, let's just do a basic, I don't know, pre-order traversal. Right. So remember, pre-order traversal, stack-based. What we'll do is we'll go ahead and put the root into a stack, How do I get a stack in Python? New stack.
But no new.
Is there a stack? I'd be surprised if there were, because usually you just use a list. Right? And then while, and what I need to do is I need to put the root in there. S.push is what I would normally use. Unfortunately, the Python folks thought that pop was an appropriate method to create, but push was not for some reason. So instead, what is push? And they don't even alias it. They should have at least aliased this. It's append, right? And then remove, you can remove from the front. So you can treat it as a deck where you're doing push-pop operations at one end or the other end. It's just that you have to call the right method. Right? And it's not a linked list. It's not an array-based list. Everything, I believe, under the hood ends up being some hash-based data structure. Again, crossing my fingers here. I'm not 100% positive on that. So I've pushed the root, right? Now, while the stack is not empty, I of course can't do that. Instead, lots of truthiness, lots of falsiness in Python. All you need to do is while s, right? While s, an empty array will evaluate to false. Any non-empty array will evaluate to true. So while I still have something in my stack, I will pop it, equals s.pop. So they do have the pop method here. I'll print it out. And then I will push, remember, right, then left, because it's a last in, first out LIFO data structure. So if you want to go left and then right, that means that you need to push them in the reverse order. So s.append root dot, or not root, but x dot right child, and s.append x dot left child. But only if they exist, right? You don't want to be pushing none all the time. So if how do I check for it's not none? If x dot right is not none, right, then do something like this. Again, what's a shorthand way of doing this? X dot right, and that's it, right? And that's way more Pythonic too. If x dot left, then do this, right? Let's see if this works. Remember, I built it so that B is the root. So a pre-order traversal should give us B, A, C. Hey, awesome. Right. Simple 3-node tree. Okay. What else do we want to do? I think that's all I wanted to do. Any questions on trees, binary search trees?
Was there like how to do like the left, right, center, or the
Left, right, center.
that kind of ordering?
Well, I mean, this is pre-order. How would you do? I mean, you'd have to do an in-order traversal, a post-order traversal, or a recursive version of those.
Is that how you make it, or just how you output it?
Well, I mean, it depends on what you're trying to do. Those three algorithms are used for different contexts.
Oh, okay.
Right? Okay. So, remember that a binary search tree also has, again, these additional requirements that there's an ordering to the keys. So that if you're searching for a particular key, you start at the root, and if the thing that you're searching for is less, then you go left. If the thing that you're searching for is greater, then you go right until you find the key that you're looking for, or you've hit a dead end because you've fallen off the edge of the tree. Okay? The problem is that regular binary search trees might be unbalanced. I could have a right child, right child, right child, right child, right child, right child, in which case I only have a linked list. Right? So our goal eventually is to build balanced binary search trees whose depth is order log n. Now remember from 156, what kind of trees have such a guarantee on their depth? Do we remember? Not ordered linked lists, because the linked lists aren't trees at all, right? They're just linked lists. But a tree who has a guarantee on a depth because it's full. That every child is there, except for possibly the last row, right? Do we remember? A heap, exactly, or heaps, okay? So again, a quick review here. A min heap is a binary tree such that the key at every node is less than both of its children. This is not a binary search tree, all right? It is less than both of its children. It's not simply less than its right child, okay? A min heap, heap, has the fullness property. All the nodes are present except for possibly the last level. And then it's full to the left, right? So that you don't have any gaps in your tree, okay? It's that fullness property that guarantees that we have a depth order log n. Not only that, but what other guarantee do we have? Where's the minimum element always going to be? Because of this min heap property here. That's always at the root, exactly. The minimum element is always at the root. The fullness property ensures that it's going to be order log n. And if you're interested on the details of those two elements, well, the first one is just simply induction and by definition. But the second one is by observing what the sum of powers of 2 are, and then solving, then reversing that and coming up with the idea that the depth of that tree, then because it's full, and it grows exponentially, that the depth ends up being logarithmic, okay? Now, there are two operations that we support, get min and insert, okay? Those two operations are the basic heap operations. Get min retrieves the root element, but you end up needing to fix the heap. How do you go about doing that? And the insert always inserts at the last possible element. That is at the deepest level and all the way to the left for where there's a space that you can put it. Right? And then you have to heapify or fix that thing until the heap property is satisfied yet again. So, come on. Let's go over here. And let's take a look at a quick example. So let's build a min heap. I don't know, 1, 3, 2. Note here that I explicitly put those out of order to drive home the point that this is not a binary search tree. This is a heap, and it's a min heap, right? But it's not a very big one, so let's continue here. 42, 10, and 8. Is that a heap? No. There's a gap there, right? This thing right here, it doesn't exist. So it would not be a heap. It would violate the fullness property. And so I have to have something there. Could I put in 1? Nope, that violates the min heap property. Okay, fine. What could I put in there? I could put in 3 if you allow duplicates. Let's just go ahead and allow duplicates for now, right? Of course, if you were to search for this and try to find something matching 3, then you would have 2 things that match for 3, okay? Now let me go ahead and insert, I don't know, 5. So where do I put this immediately? Do I start at the root and say, okay, well, 5 can't go here. It has to be a child or a grandchild or a descendant, basically, of 1 because it is larger. So do I go left or do I go right? Again, if you only look at the local information here, is there enough that you can tell that, that the next possible place that you should put it is over here? Because what if I put it over here? Is that going to be a heap? Nope. So the idea with a heap is that you eventually satisfy those properties. Your priority is going to satisfy the fullness property, meaning that you're going to put it right here. Okay? Now, is that a min heap? It's full. Yes, we've achieved that. But does it satisfy the min heap property? No. We need to go ahead and heapify or fix the heap. How do we go about doing that? Well, 5 and 42, those are the things that violate the heap property, right? So let's just go ahead and fix that. How do we go about fixing it? Swapping them, right? 5 and 42. Now is the min heap property satisfied? Yes. Right? That was simple enough. What if we were to insert another element, say another copy of 2? What would we end up having to do? Actually, no. Let's go ahead and go all the way. Full Monty there. 1, negative 1. Right. Well, where do we insert next? As the right child of 5, right, to ensure the fullness property. Now, let's look ahead here. We're going to end up swapping these two. Negative 1 still is not where it needs to be, so we end up swapping these two. We end up swapping these two. And at that point, you are done, right? So 1, 3, 5. So 1, 3, 5. What does that look like? 5, 3, 1, and negative 1. Right? That's what it ends up looking like. Now, what if we want to get min? So I guess the thing that I was trying to drive at here is that you heapify up until the heap property is satisfied, and at which point you stop, or you go all the way back up to the root. But because the depth here is guaranteed to be order log n, then all of your operations with respect to the depth are going to be log n. Okay? What about get min though? What do we do? First of all, we save it off. Save off negative 1 because that's what we're going to end up returning. Okay? Now we've got a gap. Can we simply promote 1 or 2?
First, we grab the minimum of the child.
So you could promote up 1. Will that end up working here? 1. And then now you've got a gap here. So which one do you promote up? Okay, so let's go ahead and I'll go in blue here. So 1 comes up here. You say the minimum, so 3 comes up here. And now 42 and 5 comes up here. That only works because of this particular example, right? What if this had been reversed, right? What if this is 42 and this was 5? Promoting 5 up now means that we've got a gap and the fullness property is no longer satisfied. So what do we do?
We just, Fred, we would need to move the right child to be the left child.
You're not going to be able to move children around. How do we prioritize the fullness property first?
We moved 1 node.
We move the last node, right? So 5, right? 5 is now sitting off here in the ether. The fullness property is satisfied. We put it back up here, and now the fullness property is fully satisfied. Right? Is the heap property satisfied, though? Nope. So what do we end up doing now? Now we recursively swap and promote the minimum among those. Right? So what is it going to be? 1 and 5. Are we done yet?
No.
Nope. What else do we need to do? 3 and 5, okay. Now, do we need to go any further? Nope, we're done. The heap property has been satisfied and it has been fixed. Okay. So once again, let's come over here. Ignore that. To Python. And we're not going to reinvent the wheel here either. We're going to use, by the way, the typical implementation of a heap is not to use nodes with a relationship of parent, left, right, left, right, parent, etc. It's instead to use simple arrays. So let me show you what that looks like. Here's an array. Oops, sorry. I want over here. Here's an array. How do we view that thing as a heap? Right? So I'm going to go ahead and bring it over here. and so that we can see them both. I'm not going to be able to do that, but anyway, what I'm going to do is I'm going to start writing these elements top to bottom, left to right, as you would a full tree. So 5, 3, 7, 3, 7, 4, what's next? 2, 2, 1, 3, 2, 2, 1, 3. Okay. Now, is that a min heap? Nope. But it is full, right? And all you have to do is associate with an array indices 0 through n with positions in your tree here, right? This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Now, the advantage to this is that a left child is at, if you're at index x, or let's say index k, then your left child is at index something like 2k, and your right child is at index 2k plus 1. It's all contiguous, and you don't have to worry about nodes at all. But as we already noted, is this a min heap? Nope. So let's go back over here to Python and make it into a min heap. I've already brought in this heap q. What do you think the q stands for? What is one application of a heap? A queue, a priority queue in particular, right? A heap is a good implementation of a priority queue where you're always pulling out the next one with the highest priority, right? Or in this case, the lowest value, right? That's how heap queue works, right? So unfortunately, it is not object-oriented. So if you want to take your array and you want to heapify it, change it into a heap, then you need to call heapq.heapify. And let me show you how this transforms your array. All right. First of all, is that sorted? No. Heapification, heaps are not necessarily sorted. Right? They are only a highest priority out first data structure. Instead of a FIFO or a LIFO data structure, if you take things out, then yes, it will end up being in order, one by one. That's called heap sort. But now it has been transformed into something that looks like this instead. So it's 1, 2, 2, what's the rest of it? 3, 3, 4, 7, 3, 5, 7. There we go. And so your heap, it's been heapified. Basically, it's fixed the heap over and over again. Oops. That is indeed a left child. There we go. And there's your heapified heap. Okay? Now you actually do have a heap in Python. All right, well, what can we do with it now? You can put stuff in, you can take stuff out. So how do I insert something into a heap? Well, it's like a stack. You can push things in, you can pop things out. So you can go heap q. Again, it's not object-oriented, so you don't call array dot append. I mean, you could, because it's still an array, right? But you don't want to treat it as an array anymore. You want to do heap push. Don't ask me why it's not just simply push, but whatever. Right? And because it's not object-oriented, it takes two arguments. The actual heap that you want, and it will assume that it's already a heap that you've already called heapify, and the value that you want to push into it, say negative 42. We can also push larger values. Right? And let's see what that looks like after we've done this. So predict, first of all, where's that negative 42 going to be? On the top. So in other words, in terms of an array, or in terms of a list, where is it going to be? Right at the beginning. What about that 42? That was larger than anything. It's going to be at the end somewhere, maybe? Right? And it is. Right? Okay. Yeah.
So when you want to add something to a heap, you would just add it to the array, right?
No.
But then you would do heap push, right?
You would only do heap push. You would never add anything to the array. Once you've heapified an array, everything is going to assume that it's a heap, and that any operation that you execute on it, it has to remain a heap.
Oh,
If you called heap push on something that was not an array, bad things are probably going to happen.
oh, sorry, I meant that.
Prior to heapification, it probably would end up screwing up. I don't know. Would it throw an exception? No. But it ends up not putting it in there?
So,
Yeah, it ends up not being in there. Huh. I don't know why.
Wait,
I tried, I saved it. Oh, maybe I didn't save it. Let's find out. Yep. Oh, no, wait.
oh, it's because.
Oh, all right, I tried to go on to the next thing. All right, so fine. Let's try one more time. Okay. It ends up putting it in the right place. What if I did 42 instead?
You heapify it before. Printing.
Oh, did I heapify it?
Yeah, you did.
Oh, okay.
Yeah.
Let's try it this way one more time. Yeah, it ends up putting it in the right place, but maybe 42 won't. No, it will. But I'm sure that you could find a way to break it.
So, so we have to like heap push,
You always have to heap push.
but do we heapify before we heap push? Yeah.
Well, I mean, if you start with an empty array is, by definition,
Yeah.
a heap, right?
Oh.
Maybe remember from 235, empty anything is anything that you want it to be. Vacuously true, right? For all x, piece of x is true for any universe of discourse that is empty, something like that. An empty, I don't know. Is an empty graph acyclic?
Yeah.
Yes. Right? Does it contain a cycle? No, because that would be the negation, and okay, yeah. Basically, the way I usually present it in, say, 235 is that the following two statements are correct. All unicorns are pink. All unicorns are green. Right? Those seem to be contradictory, right? But you're talking about a universe of discourse that is empty. So therefore, any universally quantified statement is true, including two contradictory statements.
That's unsettling.
So that's what happens when you've got a universe of discourse that's empty.
So,
But here in this case, an empty array is a heap.
okay.
So how do I pull stuff out? Heap q dot heap. What do you think? Push versus pop. Right?
Okay, so
And of course you have to give it the array because again, it's not object oriented. These are not methods that are in the array or the list class, whatever you want to talk about. X. There we go. And note that I'm putting that into a while loop while the array, while it's not empty. And we get 1, 2, 2, 2. Now we do get things that are in order. Right? Negative 42 through 42. Okay?
why?
Because you're always getting the minimum.
Oh, yeah.
Right.
Makes sense.
Okay? All right. Well, what happens when we have something weird like this? Oops. Again, I'm not copy pasting the wrong place. There we go. So here's my array. What is my array of, though? And by the way, before we go on, do you see that the heap was able to support duplicate values? Right? That's fine. It's not going to look at these two things as needing to break a tie. So let's go ahead and look at this one now. What's the order after I heapify this stuff?
I think by default it does the first with a double.
Exactly. Dot heap push. Oh no, heapify. What was it? Heapify. Array. And then I'm going to go into my same while loop here, and we're just going to print this stuff out. All right. I've got 5, 5, 5, 1, 2, 3, 4. Right? What about those fives? What order are those going to come out on?
Would it be
Yeah.
lexicographic order?
Well, why though? It would be 5, 5, 5. There's no way to disambiguate those. Those are all three. There's a three-way tie there.
Could it do it by the?
Then, well, it does it by the next thing because it's a tuple. If there's a tie in the first, what did you call it? Coordinate? What are they called? Coordinates? Tuple? Well, yeah, the entire thing is a tuple, but the first, second, third, each one individually is the element? Okay, fine. That's good enough. It'll go, then it'll look to that to break ties. And so I've got 1, 2, 3, 4, then 5 ABC. Okay? What happens when I introduce something weird into the mix? For example, 5 and none. All right? Where is none among A, B, and C? It's incomparable. Excellent answer. You cannot compare none with any strings. You cannot compare none with any numbers. Just like in Java, you can't compare none or null to anything, right? So what are you going to expect from this? An error, right? An exception, and a fatal exception at that. You cannot compare none to A, B, or C to understand where it's going to be. So this will happen in your heap or in your Huffman implementation if you're not careful, because only the leaves will have data that is comparable. Only the leaves will have A, B, C, D, E, F, G, whatever, right? So how do you break ties when you've got internal nodes that don't have that data? How could I break ties here? Don't use none, first of all, right? Use something that is comparable to all other strings. Just some placeholder. So suggest some placeholder. The what?
Literally none?
The truly none, you said?
Literally the word none.
Oh, like inside of a string, you mean?
Yeah.
Okay.
That would be great. Less than 10.
Yeah. That would appear between M and N and O,
Yeah,
right?
I got that.
Or you could just go, empty string, right? It just needs a way to. That's actually not a bad answer. It's just that it will end up with a different weird order, right? Here, this one's perfectly fine. ABC, or the empty string comes before anything because of lengths of strings, right? So it is perfectly fine to use tuples in a heap sort. You just need to make sure that they're comparable, or that you're using some sort of a placeholder value so that they become comparable. Now, what you could really do, if you really want to get into it, is come back over here to your node class and to do make my node class comparable. And to do that, you're going to have to implement at least two methods, LT and equal is what I would suggest, EQ, right? And then use a library to inject all other comparisons. Because to make a node comparable, given two nodes, you have to say, does this node come first, or does this node come first? Or are they equal? Or are they strictly less than? Or are they greater than or equal to, et cetera, et cetera? They're like not equal, equal, less than, strictly less than, greater than, strictly greater than. So there are at least 6 things that you have to do. You only have to do at least 2 of them, and then you can use a library to inject the other 4. Yeah.
I was able to get away with just less than.
You were? Then you never had ties to break. Okay.
Compared by weight, and I think if it's less than, no, because they're equal.
But was your tiebreaker always unique?
Well, like, is 5 less than 5? No. I mean, that's just because an answer is.
Okay. That seems icky. But I don't know.
I just.
Does it work on the grader?
Yeah.
All right, then you're good. Yeah.
I don't know. I was wondering, like, what to do when 2 things are equal in our Huffman code. Like, how will we find
That's up to you.
that one?
Right.
Well,
Break ties. If you've got 2 trees with weights 0.5 and 0.5, well, 0.1 and 0.1, right? Does it matter? Does this go on the left tree or the right tree? No. Switch them around and you get an equivalent code like we were asking about. Now instead of 0, 1, it's going to be 1, 0, right? So just make it work. Right? Break ties however you feel that you need to break
I
ties.
guess my thing is it would matter if each leaf is supposed to be like not a sum of the things that came before it.
I'm not sure what that means, but you're going to be going by the weights, and the weight of the new tree is the sum of its two children, right? Note here that you can also use objects. So of course you could have had a node here instead, node containing C, right? But there you've got to be careful because then you do have to make it comparable, because it's not gonna look at that C and say compare it to that node's A, right? So if you're going to do that and get all fancy with it, then you need to make sure that you're 100% fancy and doing all this stuff. Yeah.
So, with this, are you expecting us to make it a heap or a binary search tree?
It's not a binary search tree, and it's not a heap. You're using a heap to build the trees. It's just a binary tree. So get your hands dirty with a few attempts first, and then I think that you'll understand how to go about it.
Always compare the last, like the list.
The what?
Compare the two smallest, right?
Well, yeah, you're always looking for the two smallest weighted trees.
That's why you use a heap, right?
Yeah, that's why you're using the heap. Yep.
Okay.
Oh,
You're using the heap to build the tree. Right. Here's the. Where's this? Oh, we didn't do the pseudocode, did we?
no.
Okay, that's fine. 8 minutes. We can do the pseudocode really quick. All right, so my input is going to be, and if I screw up on this, that's okay. We'll go ahead and pull it next time. My input is going to be a collection of, I'll call them letters, but more generally they're symbols. So letters, right? Sigma is equal to, I don't know, x1 through xn with frequencies f frec of x. That'll just be the frequency of x, okay? And my output will be not the code, but a Huffman tree. What if there was a question online? I don't know who you are, but what if it was a priority heap? How will the tie be broken? It's up to you. You have to determine how you break the tie. Right? So our output will be a Huffman tree. So my initialization here, in it, right, I will create n single node trees, each with the symbol or letter x sub I, 1, and 2, a weight equal to the frequency of x. And then also with my initialization, I will place all nodes, all trees, into a min heap with using the weight. So the weight of the trees is what you're going to be using. And again, as long as the weights are all unique, you're going to end up being fine with heap Q. But if you get into a situation where you've got this tree A and this tree B, where this is 0.1 and this is 0.1, you then have to break ties somehow. So you will probably need to end up using some sort of a tuple. Right? And then while, or, I mean, you're only going to end up doing this n minus 1 times, because if I've got, say, 5 trees, how many iterations of combining two trees do I need to implement in order to make sure that I only have one tree in the end? N minus 1. Right? So I'll go into the for loop instead. For j running from 1 up to n minus 1. Right? What I'll do is I'll go ahead and go with left will be end up being h dot pop. Right will end up being h dot pop. So implicitly here, I'm always preferring the lesser weighted tree to go to the left, and the larger, if it's strictly larger, to go to the right. Oh, okay. So there's left and right, and what I'm going to do is a new node. So U is a new node with weight equal to left dot weight plus right dot weight. Right. And then I need to make U dot left is equal to left, and U dot right is equal to right. And I've run out of room at this point, so I will come back up over here, and I will put it back into the pool for consideration. H dot insert the new node U. And that's it. Right. Once you are done, all you have to do is pop out the one remaining tree and return it. Put stuff in, take stuff out. Again, when I cover heaps at the end of, say, Computer Science 2, I like to call back to the very beginning of the course. The Computer Science 2 has a theme or mantra, whatever you want to call it, of smart data structures and dumb code are a lot better than the other way around. And a heap exemplifies that. Because all we're doing is putting stuff in, taking stuff out. Putting stuff in, taking stuff out. We're letting the data structure, the heap, do all the heavy lifting for us. Right? And that's how you get heap sort. You put everything in, you take it all out, and it's magically sorted because of how a heap works. Okay? Yeah?
Why do you return h dot pop instead of just the whole h?
Well, H is a heap, and you're not returning a heap, you're returning a Huffman tree.
Oh, and since the tree would include the node, like, since you're just taking out the root of it, which will have the children.
It'll have all of its children already set up. All right?
Well,
So again, there's a lot of implied here that U dot left and U dot right, also right dot parent and left dot parent are also set to U. But those are the implementation details that you usually omit from pseudocode like we just did here. All right? So, complexity. How do we go about determining this? What's the elementary operation? Put stuff in, take stuff out. Put stuff in, take stuff out, right? So, heap push slash pop. Or insert, remove, whatever you want to call them. Okay? Each one of those is going to be order log n. Right? Plus order log n. Right? 2 times, why? This is the pop operation, times 2. Remember, we are popping. Right? And then we ultimately insert it. So 1 times this is the insert. Or actually, fine, we'll use the same term here, a push operation. So this is going to end up being order log n for 1 iteration. How many iterations do we end up doing? N minus 1. We do start at 1. So this is going to end up being n minus 1 iterations. Gives me ultimately order and log n. Now, of course, that means that you've already pre-processed everything and that you've pre-computed all those frequencies. That means that you are processing a file, and hopefully you're only going over that file once to count up the number of times that there's an A, count up the number of times that there's a B, et cetera, et cetera. And then that ends up being, you know, the size of the file, right? However many bits or however many bytes technically, because you go byte by byte, there are, right? But this is the heart of the algorithm. Now you're still not home yet, right? What you have to do is you have to then take that tree and start at every leaf, traverse all the way up to the root to actually find the code word and output the code word. But I assume that you can do that once you've got everything else. Okay?
Especially
The-
if it's a heap, does that mean it's a full tree, right?
No, the Huffman tree is not a heap. They're both binary trees, but they're different concepts. Right? The tree that we wrote, the Huffman tree that we built, that's not a heap. That's not even full. Right?
Okay.
All right.